Good. Okay, that's Wednesday. And let's take a look at what we have covered in the book. So you can locate yourself. And here you go. Here's the I'm going to put the book here on the left side and my notes on the right side. Right here. Okay, so chapter 4. Oh, let's take a look at the other chapters too, right? So here you go for the exam so far. Material for the second exam so far. 1. 1 point, chapter 1. 1.5, scalars and vectors. And I go to like that. 1.6, vector, addition and subtraction. 1.7, the components of a vector. 1.8, addition of vectors by components. Interesting. Chapter 2. No, not chapter 2, sorry, chapter 3. Chapter 2 was part of the first exam, right? Chapter 3. Kinematics in 2 dimensions. Kinematics in 2D. 3.1. Displacement velocity and acceleration. Oh, equations of kinematics in 2 dimensions. Equations. Kinematics in 2 dimensions. Three point three, projectile motion. 3.4, relative velocity. And now we're doing chapter 4. Right? 4.1. More students coming. Concepts of force and mass. Okay. Force. I'm going to put it between parentheses. Push or a pull. Mass. Quantity of matter. That's a good way of define mass. Newton's first law. Newton's second law of motion. Vector nature of Newton's second law. Types of force. No. Newton's third law. Okay. We cover Newton's third law as well. Types of force. Let's take a look here. Types of forces. Types of force. Yeah, this was a very short section. Okay. He's talking just about the non-contact forces. Types. You can skip that. Skip. You don't need to know that. And the next one. Okay, gravitational force. We didn't cover that yet. Force. I told you that the weight is a gravitational force, but there is one more detail important about the gravitational force. Okay. mg, I told you about mg, but not the next step. Okay, so we will cover that. We will cover. Yet to be covered. This is an extensive chapter yet to be covered. The normal force. We covered. 4.9 static and kinetic frictional force. Frictional force. Yeah, we covered that. The tension. Like that. Tension force. Those are just examples. For 11, it's equilibrium applications of Newton's laws of motion. We're going to cover that. It's just examples. In a way, we have covered, and non-equilibrium applications, non-equilibrium applications of Newton's law of motion. So I'm going to boldface what we covered. Those Newton's third law. We cover. Oh, so we're almost done here with this chapter, right? Let's take a look at those equilibrium and non-equilibrium applications, right? It's just a matter of, in a way, already covered because we gave some examples. Okay. Here is one example. Here's another example. Here's another example. And here, see the lift here, the lift force. That's the thrust. That's the drag. R is the drag force. Okay. And then non-equilibrium. Non-equilibrium is Newton's second law of motion. Okay, two boats, little boats tugging another one. That's one example. That's another example. That's another example here, yeah. Accelerating blocks in an inclined plane. Hoisting scaffold. Okay. Another example. And okay, so I'm gonna bold face that. So what we're going to do, we're going to spend the first hour covering this material, and then we do the third lab, okay? We'll spend the first hour lecturing and the remainder doing the lab. And I'm gonna put it lab like that. And let's take a look at the syllabus. Wednesday, 18th. Lab 3 is the first table. And by the way, let me put that here. Lab report for lab 2 is due now. Right? Make sure you upload it there to your group folder. Going back to my syllabus. And yeah, so it looks like we'll be able to finish chapter 4 now. Yeah. Okay, so let's talk about the gravitational force, right? Or the weight. Already told you that the weight is given by the following formula. Thank you. Weight, W, equal by mg. And if you want to write that in terms of vectors, right? You write like that. But there is another way of writing this equation, which is a more complete way to formulate the gravitational force. Okay? Gravitational force. There's another way. Okay, and I'm gonna put it here, instead of writing out down like a weight, I will write it down as gravitational force. Even better, I'm gonna put capital G. And I'm going to explain the difference between those two formulas. The other way, and by the way, it's in your book, going back here. Gravitational force. Yeah, it doesn't go there. Oh boy. Let's see, 4-1, 4-2, 4-3, 4-4. Then define, okay, go, that's the one. Define Newton's law of universal gravitation, okay? And I'm going to write that down in terms of vectors. Okay, and there's another way, which is a more complete one. of formulating the gravitational force like that, the gravitational force. Okay, and that's gonna write that. Notice that I'm gonna use exactly the same symbols, okay? And the way it goes is like that. Let me get, let's see if I have a good illustration for you to show you. Okay, someone asked it. Thank you, Ridwan. I'm not doing so hard. Yeah, okay. Yeah. So going down here. Okay, here you go. That's a good illustration for what I want to show you. Okay. And I'm going to do the step by step, like the movie. The movie. Here you go. Here's the Earth. Okay, and then suppose that we have an object. Doesn't have to be nearby the surface of the Earth. Object. I'm not going to object. What we know about the force of gravity is that when we have two objects next to each other, this object, one object is going to attract the other. Okay, that's the action at distance, or even better, a non-contact force. Okay, I want to put it a little bit further away. You know what? Leave like that. Leave like that for now. Like that for now. Okay. So an object anywhere feels this gravitational force due to the Earth. One way is to formulate this force is like by the mg that you're already familiar with. Now, don't forget that by the same token that the object is attracted by the Earth is also attracted by the object because those two objects are interacting with one another, okay? And when we have those two objects, you go. Separated by a distance here. I'll call this the object. Let's see. I'll call this distance R. Let's see, maybe I need, yeah, that's the one I need. Those two objects are separated by a distance R. Instead of calling this force equal to mg, we can also call it in a different way, which is a more complete one. Okay, we can also say, and by the way, I gotta do something else too here. This object has a mass m, and the Earth, has a mass capital M. We're gonna put it like that. Notice that I have a distance here as well. And I'm going to write down in my Word document first. So it's going to be given by something like that, minus big G big M, which is in this case the mass of the Earth, is small m, which is the mass of the object. And we are going to have something here that is the unit vector r hat. Okay? So what we have here, is just an approximation, and I'm going to write it down, of this more genetic equation. Is an approximation of that. Okay? The equation mg is an approximation of this more genetic equation. Okay? In the above, big G is the gravitational constant. I'm going to give you the value for it, gravitational constant. Big M is the mass of the Earth. Little m is the mass of the object, and r is the distance between the two objects, center to center. Okay, center of the object from center of one object to the center of the other one. Think about that. Remember that mg is just an approximation. Now, what about big G? Big G has a value, a numerical value, that I'm going to write down here. Must be in your book. Oh, right here. And I never memorized that, so I don't expect you to memorize either. Okay, but we can always refer that to the internet, okay? Newton, meter square, kilogram square. Big G is the universal gravitational constant. The universal gravitational constant. And it doesn't matter what's the distance between the two objects. Okay, they can be further away as well, whether it's further away or whether it's close or further away. Here you go. Like that, right? If you have something like that, then the distance r is going to be greater, right? The formula still applies. And now I can copy. This one right here. Yeah, okay, good. It's here. Okay. And here too. But in this case, it's, by the way, in this case, it's going to be plus r. R, the r hat is the vector position from the center of the Earth to the center of the other object. Okay? Okay, and okay, the magnitude, I'm going to write that down in terms of the magnitude. the magnitude of this force, okay? And that's gonna be how you are going to memorize this force. Then since it's a magnitude, we do not have a vector right here, and we write in this way. But let's not forget, this force is always attracted. Always attracted. Okay. Okay, so we can come up with an example here, numeric example. What's the magnitude of gravitational force that acts on each particle in figure 4.9? Let's see what 4.9 is. Right in here. That's the one. And is it okay? He's giving us the values of M1 and M2. Okay. M1 is 12 kilograms, M2 is 25 kilograms, and their distance is 1.2 meters. All we have to do here is to apply the formula in a straightforward fashion. Okay, so here is the equation, 6.67, 12 kilograms, 25 kilograms, 1.2 meters squared, and look at the value of this force. It's a very small force. Okay, so it's so small that you can hardly measure it. So for comparison, you exert a force of about 1 Newton when you're pushing a doorbell. So that gravitational force is exceedingly small in circumstances such as those here. So the idea here, for two objects, one of mass M1 equal to 12 kilograms, and the other M2 equal to 25 kilograms, and separated by a distance of 1.2 meters, okay? They do attract each other. They do attract each other. However, their force of attraction is very small, so small that it can't be neglected. Okay, on the order of 1.4 times 10 to minus 8 Newton. Like that. Here you go. This force becomes, important only when large masses are involved, okay? For instance, the mass of the Earth and the mass of another object. The mass of the Earth. What's the mass of the Earth? Let's take a look. Oh, here you go. The mass of the Earth, is like that. The mass, what is the mass of the Earth? M equal to 5.98 times 10 to 24 kilograms. And the mass of another object. So let's do the math, let's do the calculation. Okay, so here you go, another example. 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 An object of mass equal to 15 kilograms is resting over the surface of the Earth, i.e., a distance R equal to the big arc, that's the radius of the Earth. Let's see what's the radius of the Earth. Again, I never memorized that, and I don't require you to memorize, although, radius of the Earth, 6,371 kilometers. 1, 2, 3 meters. Calculate its weight or the force of gravity that Earth exerts on this object. Note that our result should be close to 150 newtons, right? Which is, 15 kilograms times G times 10 meters per second square. Let's see if you get that. Okay, and then a solution. And then I'm going to use Excel to do that. Let's see. Hey, Professor, I just had a thought here. You're allowed you say to download the files from Excel. Okay. I do not know, Ridwan. I never use the online Microsoft online Excel. Okay. I do not know. Okay. Check if it works or not. So, but keep in mind that if you have Excel installed in your machine, it definitely is going to work. If I use it online, I do not know. I never try it. Maybe it will work. Let me know if it, if you use that, let me know if it works or not, okay? Most likely it's going to work. I suspect that it's going to work. Okay, so let's get the roster here. And I'm going to do the math here. Big G, right? Big Emma. Big G is what? Newton meter square per kilogram square. Superscript. Kilogram. And lowercase m kilogram. Yeah. Let's see. 6.67, right? E, let's go take a look at the value. Uh, 6.67 times 10 to minus 11. E minus 11, okay? Mass of the Earth. Mass of the Earth is this one here, 10 to 24, 5.98 times 10 to 24. 5.98, 24, and here we want kilograms. In kilograms. Okay, and then we have to come up with a equation here. Big G. Oh, don't forget one more piece of information, right? The distance to the center of the Earth. 6,700. Oh, 371. 6,371,371 371, 2, 3. That's the distance in meters. Number. And now we can calculate big G, big M, small m over r squared. When we do that, that's what we get for the force of gravity, okay? Remember that I told you that this number was supposed to be close to 150 newtons, and that's exactly what we're getting. Very small difference, right? 150 here. What's the percentage difference? The difference is very small. We're getting 150 because, let's see, because we're using the gravitational acceleration as being 10 meters per second square, right? But if we use 9.8, let's see how much we get. Yeah, we get 147, just like the other one. Let's take a look at the, 147 even, just 0.4 difference. Okay. So that's what I'm getting. Solution, applying the equation, applying the generic equation. We have 147,4, or not comma, dot 4 newtons, okay? Which is very close to 150 newtons. So 9:30. Let's take a look at the hook again. There you go. There's an example. You can also calculate the force that Earth exerts on the moon. If you know the mass of the moon and the mass of the Earth. Go. Here, that's how the gravitational force decreases. We can plot. We can also plot force of gravity versus the distance. Force of gravity on an object versus its distance. Okay, but there is one more interesting thing that I didn't tell you before we go into that. Huh? Okay, so here you go. Not just note that the gravitational force decreases with distance. But we can also state that the acceleration of gravity also decreases with distance. And how do we do that? Okay. We have this relationship here. Okay. And I'm not gonna do in vector. I'm gonna do the light scale, and it's gonna be a equality. I'm gonna worry just about the magnitude of everything, okay? What I can say here, what I can do here, is that the acceleration of gravity varies with the distance from the center of the Earth. Okay? It's a function. At the surface of the Earth, at the surface of the Earth, G is approximately 10 meters per second square. Okay? But as we climb higher and higher, this G should decrease, okay? And the relationship is given by that. Look what will happen. What happens? This M here is the same as this M here. Okay? So we can cancel those two M's. And the acceleration of gravity is going to decrease with the square of the distance as you climb higher and higher. Let's see how it behaves. We can do that. I always do this plot for my students. Here you go. A distance from the center of the Earth in meters, G in meter per second square. Okay. Superscript. Okay, the distance from the center of the Earth. So we should start at this value right here. Inside the Earth, inside the crust of the Earth, the equation is different, okay? And here we can write it down. Here you go. M, big G times big M divided by R squared. And look what we get, 9.83, okay? Meters per second squared, which is the expected result for the acceleration of gravity. We're gonna put that in the regular format. I'm going to do something else too. I'm going to change a little bit my formula here so we get the right result. And I'm going to do the following. I am going to change the radius of the distance, right, from one object to another one. For every, let's see, 100 meters, 1,000 meters, right? 1,000 meters is 3,000 feet. Yeah, let's do every 1,000 meters, okay? So here you go, 6, 4, 7, 1. No, that's not 1,000 meters. That's 1,000 meters. Yeah. No, 1,000 meters is too much. Let's do 100 every 100 meters. 4, 7, 1, 1, 2, 3. Okay. Format cell, number. I don't want any decimal place, but I want 1,000 separator. Okay. See what happens for every 100 meters. For these 100 meters, there was a small change in the force of gravity, okay? And I'm going to keep on increasing the height of the object for every 100 meters. That's not 100 meters. No, that's 100 kilometers. I put 100 kilometers here. Let's do yeah, 100 kilometers is too fast. 100 kilometers. Let's put 20 kilometers. Yeah, let's put 20 kilometers so you can see. 100 kilometers is too much. I put let's see, 20 kilometers, 90. Oh, yeah, let's put 20 kilometers, every 20 kilometers. And that should be 300. Yeah. Let's do this way. That's better. Okay, so every 20,000 meters, which is 20 kilometers, we have this much in change of the acceleration of gravity. Okay, I'm going to even write that down here, percentage difference. You know, that's going to be this value minus this value, $sign, so we don't change. 100 divided okay, I should put this one here, divided by that. Okay, it's here 0% difference. What about, okay, so look here. How much percent we're changing for lower altitudes, right? And I'm going to put another column here that's going to be the height. But I'm going to put the height in kilometers. Height in kilometers is going to be this one. Minus this one divided by 1,000. And that should be a dollar sign here. There's a reason why I put the dollar sign there. Okay, 20 kilometers, 40 kilometers, see that? 40 kilometers high. 100 kilometers high is considered the beginning of space, okay? And we have only a 3% variation in the acceleration of gravity. Okay, let's continue here. As we climb higher and higher above the Earth's surface, the acceleration of gravity keep on changing, keep on decreasing. Here at 300 kilometers high, the acceleration of gravity decreased from 9.8 to 8.9, almost 10% difference, okay? And so on. At the point where we have the moon, well, we won't be able to get there to the moon because it's going to take too long. 780 kilometers, right? At 1,000 kilometers high, we have 7.34. Now, if you want to find out the acceleration of gravity at the position where the moon is, right? Distance of the moon. What's the distance to the moon? 384,400. 384,400. And this one here is going to be 383,000. 383,400. Something like that. Why it didn't do that? 300. You know what? Let's see. We're gonna be like that. Like that. Yeah, very big number. And what do we get for the acceleration of gravity there at that distance? Wow, it's very small because it's very far away. See that? And I'm going to put that in scientific format so we can see, yeah, in millig's. Yeah, in millig's. We can plot the acceleration of gravity against, just like the book did, right, against the height in kilometers, right, until 1,000 kilometers high, insert. You're gonna get something like that. That looks like a linear, but it's not linear. Let's see. 7. Yeah, it's not linear. If I keep on increasing here, you're going to start to see the sort of concavity here. Let's keep on increasing. Let's see. One more student coming in. Insert. Yeah, start to see a concavity here, okay? The book kind of exaggerated. Okay, but that's because he's doing in millions of meters, right? 5 millions, 10, 15, 20 millions. But as I'm doing a very small section of this graph here. Okay, 942 right now. And okay, relation between mass and weight. I did that for you. Okay, and we covered that. So we're done with chapter 4. I want you to do other problems on your own, okay? Oh boy. Okay, this problem here is an interesting one, right? You can have 3 mass configurations here. And what's going to be the net force applied to this object? This mass one is going to attract mass 3. This other object is going to attract mass 3. And the net force, is going to depend how high this mass is compared to this one and the distances, okay? So let's see. Check your understanding when a body moves from sea level to the top of a mountain, okay? What changes? The body mass, its weight. The weight changes. Okay. 2 objects with mass m1 and 2 are separated by distance 2d. This one right here. Mass 2 is greater than mass 1. A third object has a mass m3. All 3 objects are located on the same straight line. The net gravitational force on the third object is going to be 0. Which one of the drawings correctly represents the locations of the object? Okay. Let's take a look. Okay, here the object is exactly at the middle. But because this object has more mass than the other, the force to the right is going to be greater than the force to the left, okay? So that's not A. In this case, the force due to this mass 2 is going to be greater than the force due to the mass 1 because it's closer to mass 2. It's not going to be net force is equal to 0. Here in this case, mass 2 is attracting m3 to the left. And mass 1 is also attracting m3 to the left. So there's no net force equal to 0. So the only one that's left is this one here. Okay? In order to have a net force equal to 0 applied to M3, M3 must be closer to the less massive object. Okay? And that's what's going to be the answer. This is a qualitative problem. And it doesn't, you have to remember the equation, how it works, goes with the inverse of the square of the distance, right? And you can conclude that should be the final answer. And now we are done with this chapter. Let me go right in here. Gravitational force. And I want to take attendance right now, and we can have our break. There is the 18th, this one here. Skype, Abraham.
Here.
Thank you. Next is Tessa. Are you there?
Here.
Thank you. Destiny Garcia.
Here.
Next is Gael Garcia. I don't see Gael. Ridwan Harrison. Ridwan? Okay, I'm gonna put a star here in Ridwan's name. Ashley is on. Thank you. Norberto Lopez. Okay, Ridwan. Okay. Next is Annabelle Madrigal.
Here.
Thank you, Annabelle. Vanessa Mena.
Here.
Okay. Catherine Pacheco. I don't see Catherine. Okay. That should be 0. Camden Park. Hello, Camden. Camden must be away from his computer. Victoria Preciado. Hello, Victoria. I don't see her. Alexis Richardson.
Here.
Thank you. And Marcos Sanchez. Okay, 10, 11. Good. So 9, almost 9:50 right now. So let's do our break from 9:50 a.m. to 10:05 a.m. Okay. Don't have any questions? We can go for the break now. Any questions? Okay, let's go for the break. I see you in 15 minutes. Okay, well, let's go back here. Just a reminder, right? The exam is going to be 2 weeks from now, 1st of November, the second exam. I'll be posting this updated syllabus soon there. And now we are going to our lesson. Drive. Right here. Did 6 and group 1, group 2. Oh, let's make sure everything is fine first. But I share that document with you all. It's like good. Looks good. Oh, wait a minute. Okay. Good. Okay, looks good. One more. Okay, group 2. Oh, yeah. Gosh, serious. Thank you. Let's see. This one here. 2. Group 3. Group 4. Group 5. Good. So everything is in there. in your group folder. Make sure I shouldn't correct lab 1 and 2. Okay, I'll be correcting it soon. I don't see lab 2. I don't see the hard copy, right? The Word document for lab 2 of group 1. Okay, group 1. Let's see, group 2 here. Okay, I don't see the hard copy either. I don't see lab 2 for group 2. I'll read one what happened. Lab 2 here. I don't see lab 2 here in your group folder. Let's see, group 3. Okay, group 2 has everything. Lab 2, group 4. Let's see. Okay, 2 and 2. Okay, good. And what about group 5? Okay, everybody but group 1 or 2, right? 1 and 2. I'll be correcting those labs soon. Let's see here, sample. Lab 1, yeah, lab 2. Good. Let me see here. Just trying to find the link in my 500 plus tabs. Okay. Was there? Okay, group 2, right? Yeah, okay, read 1 and read 1. Okay, good. And group 1, were you able to upload it?
I'm uploading it right now.
Okay, I see lab 02 here, but I don't see lab 01, the hard copy for the Word document for lab 01, okay?
That's the first one. I don't know why it's named Lab 2, sorry.
Okay, so that's supposed to be the first one?
Yeah, I just renamed it.
Okay. So let me refresh here. Yeah, okay, good.
I'm just screenshotting the data for Lab 2 right now.
Okay. So let me fill you in this experiment. Okay, I need you to have an idea how this experiment is performed. Okay, I'm going to show you the experimental setup in the videos that we have available. Lab 3. Oh, I see. Today is 18th, right? I'm looking for something in my notes and I'll get back to you. And so on. Okay. Okay, the situation is like that. We have a force table, which is just like a protractor type of table. And let's take a look at YouTube. Here you go, force table experiment. Okay, here you go. Exactly like that. Okay.
I'm a full-time CTO without knowing how to code.
I'm the founder myself. Built the company over the last.
Here you go. Experiment vectors on the force table. Let's see, additional forces.
In this laboratory.
Okay, I want to have an idea how it looks like, okay? So the force table is just like this device that you see right in here. A circular table with protractor on the top of it. Okay, I'm illustrating this force table like that. Okay, I didn't put the graduations here, but you're supposed to have the angles imprinted on the top of this force table. Why force?
You will investigate the addition of force vectors.
Yeah.
The objectives for this laboratory are: use the force table to determine the vector sum of two perpendicular forces. Compare experimental values with calculated values for the magnitude and direction of a resultant force. And use the force table to demonstrate the vector addition of three forces. To conduct your experiment, you will use a force table with pulleys.
Okay, so here's the equipment that we use for this experiment, and I'm going to document here in my notes. Okay, lab 3, force table, equipment. I'm going to center justify that. Equipment, and here we go. Force table. First table, circular table. You know, let's put it this way: circular metal table with a protractor on the top of it. We need to know what the angles that the force are being applied. That's why we have the protractor there at the top. Okay, going back here. Here you go. See here the protractor here at the top, right? And we also have this little pin here sticking out. There's a reason for that. And you can adjust the heights, can level the table as well. Okay.
Ring and strings and mass holders.
Let's see.
You will use a force
So
table.
we have also the string here, the ring with the strings. Let's write it down. Ring and string, ring with 3 strings. The picture here show you can use with 4. There are 4 here because he's using four forces, right? But if we use only 3 forces, we're going to need only 3 strings. And what else?
I have a question.
Yeah.
So this ring and 3 strings demonstrates gravity level?
We're going to get there. We're going to get there. Here we're just listing the equipment that we're using, and you're going to understand soon how this ring is used. Okay, just hang in there for now. And what else? Pulleys. Ring with 3 strings. Let's see, 3 pulleys. And the pulleys are those ones right here. Pulleys with a support that we attach it here at the edge of the table. So here you go.
To conduct your experiment, you will use a force table with pulleys, a ring and strings, and mass holders and slotted masses.
Okay, so we have this other one as well, mass holder. 3 mass holders. 3 mass holders. They're usually 50 grams each mass holder, 50 grams each, okay? Assorted slotted masses. Okay. Three mass holders to produce a force, okay? And here too. In the slotted masses, also I used to produce a force on the table. Not on the table, but on the ring, okay? This is a force on the ring, 3 pulleys to hold the mass and pass the string. Okay, so here you go. Set up.
Set up the force table according to its instruction manual.
Okay, here's the first pulley. You can clamp. Here's the pulley. You can clamp the pulley anywhere here in the device, just like I have in my own. Here you go. In my own slide. In this case, I put 2 pulleys at 90-degree angle. Okay, I choose 90-degree angle because we can verify the Pythagorean theorem. And then the third pulley goes here to cancel all the summation of the forces right in here. Okay, so here you go. See that? Here's the ring for, okay, Camden? The ring is sort of a support. It's just a support that we use for the masses. So we have the ring and the string, right? The string, we pass the string through the pulley and the clamp, right? And then at the end of the string, we hang the masses with the mass holder. Let's go back there to our, and she's gonna do that.
And become familiar with its operation.
So she's setting up the pulley. Okay, okay, here you go. See this, the ring here? The ring here is exactly to ensure, you know, it's part of the whole setup to apply a force to the system. The ring ensures that the device doesn't slide off the center of the table. And here you go, here's the mass, the slotted mass plus the mass holder. Okay. And in our experiment,
You will use.
He's doing exactly the way I do, okay? You set up a force, 2 forces at the angle of 90 degrees, and then find out what would be the equilibrium force, the force that cancels the other 2, the vector force that cancels the summation of the other 2.
Use the force table to determine the magnitude and direction of an equilibrant force that balances the vector sum of 2 perpendicular forces. And you will calculate experimental values for the magnitude and direction of the resultant force. Then you will compare your experimental values to the actual values. Attach 3 pulleys to the force table and 3 strings to the ring. Hang a 50-gram mass hanger from each string. Label the pulleys and their associated hangers A, B, and E. The weights of masses hanging from the strings will exert forces on the ring in the directions of the pulleys. Record the masses and directions for the forces that will be applied by hangers A.
We are going to do a similar table here. Well, I'm not calling A, B, I'm calling 1 and 2.
A and B.
Okay, so here you go. If you go to the, not this one, lab 3, make sure you have lab 3 there, right? There you go. The spreadsheet of lab 3. Okay, table 4, see, I put M1, M2, and M3, right? Theta 1 is the angle that M1 makes there in the table, as measured by the protractor. Theta 2 is 90 degrees. Okay, and theta 3 is the one that you find. Those 2 remains fixed. Notice that I don't change the angle here, 0 degrees and 90 degrees, right? What I change is going to be the amount of mass that goes here. No, the amount of mass that goes here. Okay? M1 remains constant, M2 changes. Theta 1 and theta 2 stays constant. So situations like that. Okay. You know, clamp, pulley, number 1 at a 0 degree angle. Okay. Clamp pulley number 2 at 90 degrees angle. That's theta 1 and theta 2. I'm gonna write that down here. Theta 1 and theta 2. Place ring at the center of the table. Okay. Pass string 1 through pulley 1. Pass string 2 through pulley 2. I'm gonna do that for 3 too. Okay. Clamp pulley number 3 anywhere opposite the other two pulleys. The angle is gonna be theta 3. Okay, the problem is the following, you know. Given a constant theta 1, angle theta 1, theta 2, giving a constant angle, the angles theta 1 and theta 2, and a constant mass, M1, right? Vary the mass M2 and find the point, the angle and amount of mass M3 required to equilibrate the system. Okay. So the situation is like that. Given given theta 1, theta 2, M1 and M2, find, that's the problem that we have, the experimental problem that we have. Find theta 3 and M3. That's how the problem is all about. That's how this experiment is posed to you all. Okay? And I'm going to repeat here, right? Constants. Theta 1, theta 2, and M1. Variables M2. Find theta 3 and M3. That's how we do this experiment. Okay. Here's 300. Notice that the values are the same here. The angles are the same, 0 degrees. Okay. And what changes here is the mass number 2. Okay. The angle of 2 remains the same. Find the angle of the equilibrium force. And look also for the lower and upper values of M3. Every time we perform the experiment, we can find an upper and lower values for M3. Okay. So here we go. If the system is not in equilibrium, the ring is going to be displaced. And there is a pin here in the middle of the table to ensure that the ring doesn't move away. Okay. Now see the illustration here in the pulley, right? That's the clamp and that's the pulley. When I put the masses, the mass holder here, you know, I see something like that. Okay. Notice the difference, right? I install the mass holder with the masses, right? So the challenge here in this experiment is to find the angle of equilibrium. And there's a proper experimental procedure to find that. And the amount of masses that you end up having, okay? So here you go. Here's an example. Mass 1 is producing a force F1. Mass 2 is producing a force F2. And you end up with this resultant force. We want to center the ring. When we center the ring, we have what we call an equilibrant force, which is going to be M3 at the proper angle theta 3. That's what the experiment is all about. I'm going to give you what you need to know here. Protractor, resolution is 0.5 degrees. Mass, the masses are measured with a scale having a resolution of the same scale that we used before, 0.01 grams or 0.12301 kilograms, 5 decimal places. Are measured with a scale. It's the same scale we used before, having a resolution. And then what you have to do, okay, because we have two masses at a right angle triangle. Here you go. Right angle triangle, see that? Right angle triangle. This resultant mass is going to be given by the hypotenuse, the Pythagorean theorem. Okay. Pythagorean theorem proves this experiment, right? This experiment in the following way. Okay, so it's going to be like that. F3 square is going to be equal to F1 square plus F2 square. But let's not forget that those forces are given by what? M3 square G square, right? The force is given by the mass times acceleration of gravity. M1 square G square. M2 square G square. Cancel the G. And what should we do? We should plot, okay, M2 square in the x-axis, M3 average square in the y-axis, okay? Again, in this experiment, we get a range of values of M3. The lowest possible value that the system equilibrates, and the highest possible value that the system still equilibrates. We have this range of values because of friction in the experiment, the effect of friction. Okay. In this experiment, we get a range of values for M3 due to friction. And this range of values will be M3 lower, right? and M3 up. Like that. Did I put that? Let's keep consistent, right? M3 lower, okay. M3 upper. That's good. And notice that we have different angles here. If you look here at the top, right? We have different angles. What's the next table? What's the next table? I have M2 here. Okay, those 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's right. Those are all raw data. All raw data. Everything else that follows are going to be results. So I calculate M2 squared. Okay? That's what this column is all about. I calculate the average, M3 average. Take the average of those two values. And then we calculate M3 average square. Why is that? Because we're going to plot M2 squared in the x-axis and M3 average squared in the y-axis, okay? So the first thing that you're going to do in this experiment here is plot M3 average square along the y-axis and M2 average square along the x-axis. On the x-axis. Okay? If we do something like that, what should we get? Okay, I'm gonna M3 square is my y coordinate. M2 square is my x coordinate. We should get a straight line with a slope 1 and intercept M1 square. M1 square. Okay. Let's do that together. This one and this one. Insert chart, okay? Looks like a straight line. Let's get the trend line there, display equation, blah, blah, blah. Okay, see that? Remember, this is actual data points, okay? Experimental real life data experiments. I didn't change anything. The slope is very close to 1. And this intercept should be very close to M1 square. Okay. So let's take a look here. More. Oh, the slope, right? I'm going to put it the slope there, 0.9398. 0.9398. 6% difference. And then the intercept, 0.0917. 0.0917. How much percent difference? 1% difference. And we have to plot another graph. Okay. M2, the ratio of M2 divided by M1, just like you see here. Don't forget, those are all results, right? Here you go, that's the one. Tangent of theta 3 versus M2 divided by M1. Let's insert it. Chart, here you go. Another straight line. Are we supposed to get a straight line? How do we get that? Going back here, right? Theta 3, let's say is this angle here, okay? M2 divided by M1, right? Is this angle here. So that's gonna be M2, that's gonna be M1. M2 over M1 is theta 3, right? Another relation.
Wait, the horizontal one is the M1.
Let's take a look at here again. Yes, the horizontal one is M1.
And then the
Yeah.
vertical one is M2.
Yeah,
Okay.
because see, F2 is in this vertical direction and F1 is in the horizontal direction.
Okay, thank you, Professor.
M2 divided by M1 is the angle, tangent of angle theta 3. So going back, another relation. M2. Tangent of theta 3. Like that. And what am I doing? I'm putting this guy here in the x-axis and this one here in the y-axis. So it's like that. X and y. Right? So when we plot that, we should get a slope of 1. We're supposed to get a slope of 1. Did I get a slope of 1? Let's take a look. A trend line, place our square. Yeah, I'm getting 9% difference, 1.09. I have to, don't forget, I have to optimize here this space, right? The intercept seems to be very close to 0. So that's the first step. First step. Now plot the two graphs, right? One, steps. One, plot the two graphs. Two, log the slope and intercept. And then last table. On the last table and obtain the percentage difference. Percentage differences. Don't forget to put the units here, right? We have units here, units here. Then you're going to get a relation, right? Number of data points, the y versus x, the regression equation, r squared. From those values, you determine the CL. The units again, okay, so you gotta look here at okay, what's the unit for M2? What's the unit for M2? Hello, Tessa. What's the unit for M2?
I don't remember for sure. I'm sorry.
Oh, that's, what are you doing? You're measuring what? Okay, M1 is what? What's the unit for M1? It's already given that to you, right?
Yeah,
What
M1 is just kilograms.
Huh?
M1 is just kilograms.
Yeah, that's right. What's the unit for theta 1? It's
I don't
here,
know.
right?
Sorry.
It's in degrees, right?
Yeah.
So it's the same thing here, right? The units for the mass here is mass of 2, mass of 3, right? So it's going to be in kilograms as well. Degrees, degrees. And then from that, you can do the rest, right? The square of the mass, what's the unit for the square of the mass, right? Average of the mass, what's the unit for the average of the mass? The square of the average of the mass, and so on, right? That's, you can get some water here. And so on. In those cases, you do not have any units, so you just put 1 here and 1 here, right? Unitless units. Unit of mass divided by unit of mass is 1. And the tangent has no units whatsoever. Okay, and then the slope, the units of the slope is just the unit of the rise divided by the unit of the run. In the case of the intercept, I want you to figure that out, right? And that's what you have. That's the first thing. Of the slope, the intercept. Plug all units. 3. Display the proper number of sig figs, right? Fill up the regression equation and R square find the CL. That's what you have to do for today. 10:45 right now. Let's see how we are doing. And this one is gonna be my number 6. So first thing I wanna know if you got the spreadsheet or not, okay? Sky, did you get the spreadsheet? Sky is not here. Huh. Okay, so I'm gonna put a star here. Okay. Tessa, did you get the spreadsheet? Did you download the spreadsheet?
Yeah.
Okay. Okay, the next question is, did you plot the graph?
Yeah, I did the 2 graphs.
The 2 graphs, okay. Next, find percentage difference. You find the percentage difference for the slope and the intercept?
Yeah.
Yes, Joe? Are you done?
I just haven't filled out like the units and then the
Okay.
confidence level.
Okay, so next here is gonna be units. You're working on the units, right?
Yeah.
Okay. So let's go for the next student, Destiny. You download the spreadsheet?
Yes, I did.
Okay, did you plot both graphs?
Yes.
Did you find the percentage difference?
No, I'm still working on that.
Okay. So let's go for Gaia, it's not here. Next, Ridwan, did you download the spreadsheet? Hello, Ridwan, are you there? Oh yeah, the only thing I'm working on is CL, okay. So spreadsheet, graph, units. So you did finish the sig fig, right? And the CL. Working on the CL right now. Ashley Izumo, you download the spreadsheet, Ashley? I'm working on the units right now. Okay, thank you. Next is Norberto.
Yeah, I downloaded the spreadsheet and I graphed. I'm just working on the units.
Working on the units. Did you find the percentage difference and working on the units? Okay. Annabelle.
Yes, I downloaded the spreadsheet. I just did the graphs, but I still need to find the percent.
Okay, so you're working on the graphs, right?
Yeah.
Okay. Vanessa.
Yeah, I did everything except for the percentage difference. I'm working on that right now.
Okay, so working on that. But did you do the units as well?
Yeah.
Oh, you did. The sig figs?
No, not yet.
Oh, not yet. Okay. And not the CL either, right? Neither the CL.
No.
Okay. Okay, Camden,
Yes.
did you download the spreadsheet?
Yes.
Did you plot both graphs?
Yes.
Did you find the percentage difference?
No, I'm still working on that right now.
Okay. Okay, and now let's see, Victoria Preciado is not here, right? Alexis?
But Professor, I have a question.
Yeah,
So, if I type the slope value, then this percent difference is going to be changed, right? Like automatically. Oh,
Yeah.
okay.
change automatically. It should be low, right? Less than 10%. Are you getting less than 10%?
No, not yet. I just need to type it, I think, right
Okay.
now.
Okay. Okay, next is Alexis. Finished everything? Yeah, why? Yeah. Okay, tell me what is the percentage difference you're getting for all the three different values. Two slopes and one intercept, right? What are you getting there for the percentage difference, Alexis? You did the graphs, yeah. And what about the percentage difference? Did you get the percentage difference? Oh, not yet. You're working. Okay, what about the units? Did you do the units? Okay, I'm going to assume that you didn't do the units, you didn't do the rest, okay? And you're still working on the percentage difference. Marco Sanchez. You get the spreadsheet, Marco? Still working on percentage difference. Okay. Graphs. Okay, good. So 1053. I want to take a little break. Okay, and let's break 10:55 a.m. to 11:10 a.m. Okay. -50. Okay. So I see you in 15 minutes. I'm back here. Okay. So at this point in time, I hope you have advanced, right? Any questions about this spreadsheet?
Professor, can you explain to me how to get the percentage value one more time?
All you have to do is to type the values. Here you go.
I understand that it was like rise over run, but like I forgot what value needs to be the rise and run. I thought rise would be the m to m sub 2 square should be the x.
Let me see. What do you want to know? Do you want to know how to find the percentage difference here, or you want to know the units?
The I guess both, because like I was like talking to one of my teammates, I mean the group teammates, and I realized that my value is kind of off, so compared to her, and I know she did it right.
Okay, so here you go. You have two graphs here, right?
Mhm.
There you go. This graph here is for M3 square and M2 square, right?
Yeah, I did that one.
Okay, the slope is this value here, this numerical value here in the equation. Do you see
Right.
here? 9398. In my case, it's 9398. So I enter here 9398. Okay? 0.9398. Did you do that in your spreadsheet?
Not yet, but
Okay.
but since like I have I plotted two graphs, which one should be?
Well,
Okay.
Okay. This one is for M3 square. This one is for the tangent. Okay. There will be a slope for the first graph, and there's a slope for the second graph.
Wait,
Then
let me
there's
see.
an intercept for the first graph and no intercept for the second graph. You gotta keep track which one's the first, which one is the second graph, right?
Oh.
Okay. Does it help?
But when I type the values on units, I mean, I don't know if in order to get the percentage difference value to convert the format and stuff. If I don't, I mean, when I type the values on units, right? Then it would automatically.
One thing at a time, right? Let's do one thing at a time, otherwise it becomes too complicated here. I want you to type the value of the slope of the first graph here. Can you do that?
Oh yeah, I did that.
Okay, what value are you getting for the percentage difference?
It's like 1.250.
It's
that's
great.
wrong. Yeah,
Okay,
that's wrong.
Wrong? Why is it wrong?
Is it wrong, or I don't know?
No,
It's
it's
kind of
right. It's
different.
correct. See, I'm getting 6.02%. You are getting better than I did.
Oh, okay.
Your percentage difference is only 1.2%. Is better than mine. Okay.
Okay.
What about the intercept? Did you type the intercept here?
Let me see. I think this one is wrong, to be honest. I got like, yeah, it's like 998, so it's like 100% wrong.
Okay, the intercept you're getting 900%.
Yeah, that's totally wrong.
Okay, so okay, did you look again at your equation here, regression equation? What is the intercept here in your regression equation?
Intercept, the y value?
Yeah, the intercept.
It's like
you have an equation.
0.8307x plus 0.
Okay, okay, so there's something wrong there. 0.83 doesn't make sense. Your
How
group
do you
number.
group number 3?
Okay, so here you go.
How do I plot the? Yeah, I'm gonna delete this one.
Okay, so I'm gonna plot it here, exactly the same data that you have, okay?
Mm-hmm.
Okay, so here you go. M3 trend line R square. Okay, I'm not getting 0.8. I'm getting 0.1. Okay, it's the same data that you have there.
Wait, is it? Let me see.
Huh.
Yeah, that's kind of strange. Can you show me how to plot the graph one more time?
Okay,
With what?
you're group number
Yeah.
3, right?
Yeah,
Okay,
I'm trying to contrast.
group number 3, here you go. M3 average square, M2 square.
Mm-hmm.
Okay, that's really good. Insert chart.
Uh-huh.
Okay, is that what you're getting?
Yeah, let me see. I'm trying to plot everything. Oh. Let me see. That trend line. Oh yeah, now my value is like same as yours. 0.9955, right?
What is this value? 0.995,
The
what's
second
that?
one? Second one, I cannot really tell, but
Okay, 0.995 is R square, okay? R square
yeah,
is 0.995, but I don't want 0.995. I want the slope, that's the slope, see here?
yeah, the slope is same now.
Yeah, and this is the intercept. Did you type the intercept there in the other one? In the other table?
Not yet, I'm about to do that. Yeah, now it's like 16.444.
Okay. So now you got it the right value, 0.10, what else? 0.1048.
0.1048. How about the
Yeah.
slope? Slope should be 0.9875, right?
Well, the slope that I'm getting here is 0.7162, okay?
Okay.
0.7163. Looks like you don't have a good data. It's almost 30%, but there's nothing you can do about that.
Wait, you got 30%? I thought, wait, let me see. Yeah, I think that's wrong. I mean, I was wrong.
What you
So
type there is whatever you get from this equation, right?
yeah, so I got 28.380 now.
Yeah, okay, just like me,
Okay.
28.380.
Yep.
Okay.
Thank you so much, Professor.
Three, that's the one. Let's see here. See. Delete that. Okay, so anybody, let's see how you're doing here. Okay, let's go to Tessa. Tessa, did you finish the units, Tessa?
Yeah.
Okay, what about the significant figures?
Yeah, I did that too.
Okay. CL, confidence
I
level?
did almost all of them. I found like the N, Y, and then R squared. I'm just having trouble finding out like the minimum and maximum value for the confidence level.
Okay, do you need help with that?
Yeah.
Okay, so you're group number 1, right?
Yeah.
Let's take a look here. Group number 1. Okay, let's see. You plot the first graph, M3 square, M2 square, insert chart, here you go. That's what I'm getting, and then you gotta have the regression equation here. Split square, okay. Did you get that? 0.9893.
I got the same.
Same, right? Okay, so for the CL is okay, right here. 6 data points. Y is going to be that equation that I got. Oops. Okay. And the R square, you have to type what you have here, 9938. Okay. Now that you have N and R square, you can find the CL lower bound and upper bound. Okay. So you gotta go in that table.
So is N though, it's just like how many data points there are in the graph, right?
Yeah, how many data points you have in the graph and R squared. You're going to need those two numeric values to find the CL, right? And you need the table too, right? You have the table there. Do you have the table there?
Yeah.
Okay, confidence level right in here. 6. 6 is this row. Okay, and group 1, 9938, R squared 9938. 9938 is between those two values here, right? So the lower bound of the CL is this value here. And the max, right, or upper bound is this one here. 1 minus 10 to minus 4, 1 minus 10 to minus 5. So you go ahead and type it in your table. But you gotta put equal 1 minus 10 to minus 4. Uh-oh, something wrong here. 1 minus 10 to minus 4. I forgot to raise here. Here you go. And the other is 1 minus 10 to minus 5. Okay? Then you do the same for this other one here.
Okay, I'll do that right now. Thank you so much.
Okay. Next one. I was talking to Tessa, right? And what about Destiny? Last time you were working on the percentage difference, Destiny? I don't see Destiny here. Okay, Destiny seems like she left, huh? Left. Or 11:23. I'm gonna put a star here. I was not here. Let's see. Read one. Last time you were working on the CL, right? See here. You got it? You finished? Okay. Do you have any questions, Read one? Oh, the units now. Okay, so let's put here units. Okay. Ashley? Last time you were working on the units, Ashley? CL right now. Okay. Working on the CL. Okay, good. Norberto?
Yeah.
Okay, well, did you finish the units?
Yeah.
What about the sig figs
Yeah.
and the CL?
I'm just looking at the table to get there right now, but yeah, I'll be done with this soon.
Okay, good. Annabelle?
Yes.
Okay, you have the graph plotted.
Yes, I have the graph plotted.
What about the percentage difference?
Yes.
Okay, what about the units?
As well as the units.
I didn't understand. What did you finish?
Yeah, the units too.
Okay, sig figs.
Yes.
And what about the CL?
The CL I didn't get. That one I'm still working on.
Okay, she worked. Okay, good. So Vanessa,
I'm working on my confidence level. I got the significant figures though.
okay, so you got everything. You found the percentage difference, right? Sig
Yeah.
fix, and they are working on the confidence level. Okay, good. Catherine Pacheco. Okay, looks like Catherine Pacheco just arrived here. Okay, I'm gonna put a note here, Catherine. Arrived at 11:20, right? Okay, we're working on the spreadsheet for lab number 3, Catherine. You download the spreadsheet? Yes. You plot the graphs? Okay, I'll get back to you soon. Okay, I'll let you work a little bit more. Come then. So did you get the percentage difference?
Yes, I did everything, I think.
Oh, you did everything? Okay. Okay. Okay, so
But I have a question.
yeah.
So, when you do the confidence level, do you have to write the like the final value or the like a minus 10
It
to
is
the
easier. It's easier for you if you do that. You write that way that I wrote. You know, it's easier because the Excel does the math for you. Instead of keep on counting the 0.999, you know, it's easier for you to, you know, do what I did, right? Let's see, where is
Okay.
that? You know, let's say equal 1 minus 10 to minus 4, right? Suppose
Mhm.
it's easier instead of for you to type 0.9999, you know, it's easier for you to do exactly how it's there in the table.
Oh,
Okay.
okay. Okay. Thank you, Professor.
Okay. And let's see. So you finish everything. Victoria is not here. What about Alexis?
I'm missing the CL and the units.
Okay. We need any help with that?
It's okay. I'm still working on it.
Oh, sorry. Oh boy, I hope I get better soon. I was just sneezing like that the whole night, trying to sleep. Never, long time I don't get that bad. But let's go for the next one. Marco Sanchez. Hello, Marco. Oh, working on CL, okay. So you finish everything else, right? Okay. 11:29. Half an hour more to go. That is not here, right? Okay, Tessa, did you manage to finish the CL?
Yeah, I finished it.
Okay. Okay, so if you want to do any questions, do you have any questions?
No, I think I did everything that it required.
Okay. So if you want to leave, you can leave. Okay, and Destiny is not here. Kyle's not here. Okay, Ridwan, you are working on the units, right? Did you finish already or still working? You got it? Okay. Okay, so let's see. Ashley, let's go to the next one. Ashley, did you got the CL, Ashley? Oh, yes. Okay. Do you have any questions, Ashley? Oops. No? Okay, good. So if you want to leave, you can leave. Right? Or you might want to work together with Ridwan. Helping him out is the units. He is your group. Norberto, did you finish the CL?
Yeah.
Okay. Do you have any questions?
No, I'm good.
Okay. So if you want to leave, you can leave. And Annabelle,
Yes, I just got it.
you got it? Okay, good. Any questions?
No, thank you.
Okay. So next is Vanessa.
Yeah, I got it.
Okay. Any questions, Vanessa?
No, I'm good.
Okay. So if you want to leave, you can. Come then finished, right?
Oh, actually, I didn't finish the tangent part. I just
Okay.
realized that.
Yeah, make
Yeah.
sure.
How do I do that?
What do you want for the tangent? What do you need to do for the tangent?
So I
Plot the
didn't.
graph, right?
Yeah, plotting graphs and everything.
Okay.
I just checked my classmates message, and then I realized that I didn't do that part, and I also the unit.
Okay. Plot the M2 divided by M1 in the x-axis and tangent of theta 3 in the y-axis, right? Tangent, oh, here you go. Tangent and M2 over M1. You repeat everything that you did for the other one for this specific graph.
Okay. Give me a second.
Okay.
Well, I need to select tangent first, right?
Doesn't matter.
Oh, it doesn't matter. Okay. I think I got the graph and everything.
So let me move forward. So I'm gonna put it here that you're working on the graph.
Yeah.
Okay, graph. And okay, Victoria is not here. Alexis, you managed to finish the unit and the CL?
I think I got the CL for the first graph, but I'm having trouble with the second one.
Okay, what's the problem that you are having?
I just don't think I don't think I'm doing it right.
Okay, so let's see what's going on. Group number 4, right?
Yeah.
3, group number 4. That's for the tangent, right? Okay, let's see here. Okay, you gotta plot this one here. Okay, insert chart. Oh, I see. That's because you don't have good data. Is that what you got there?
Yeah, that's what it looks like.
Yeah, okay, so yeah, this one looks like a outlier. Looks like this one is the outlier. But let's see. Don't desperate. If you were doing those experiments in the classroom, I would ask my students to do that all over again. Okay, so this slope here is a good slope, but this intercept here is off. Okay. Now the question is, which one is the bad point? Is this one or this one? Okay, that's the question. Definitely this one is off by a lot. This one is 7% off only. Let's see which one. I'm going to eliminate those two. Okay.
Wait, is this right?
But let's see. Let's see a little bit. Can be the problem can be this one too. I suspect that's the problem. This one here is the problem. I suspect. Let's see. Let's plot again. Insert. No, I got the wrong one. Let's see here. You know what? Go ahead, type what you have there. Who am I talking to? I cannot figure out which one is the outlier here, but might be this one. Let's see. Let me change the format here so I can read those more easily. Format cell number. Okay. Okay, good. Now, is it increasing or decreasing? Ah, yeah, is it increasing? That's good. So it must be this point here, 0.66. Yeah. Okay, let's try to plot without that pair. And let's see what we get. Okay, I eliminated that point that seems to be the outlier. Seems to be the outlier. No, that's not the outlier. Okay, maybe this is the outlier. Let's see. Insert. Man, those guys didn't do a good job. Those guys who collect this. It looks like this point is not a good one. Yeah. Yeah, it looks like this point is not a good one either. The last one. Now let's eliminate that from the plot and let's see if we get a better result now. Yeah, it looks like everything is bad here. Yeah. Okay, so go ahead and fill up 0.93, right? And 0.3436. That's wait a minute. That's the tangent. Oh, this is the tangent. Oh, why am I doing that? Yeah, this is the tangent. You don't have to worry about the intercept. All you have to worry about is the slope, okay? But even though we have this, what seems to be an outlier, you're still getting a good value for the slope. The problem is the intercept that's somewhat off from the expected value, okay? But
I was just looking for the CL.
you're looking for the CL? Okay. So let's do the CL. Let's do the CL together. I have the CL for the tangent, 0.9015. That's what I have, right? The N is 6. Okay? You do that?
Yeah, I got that.
Okay. Now let's go for the table. Here you go. Here's the table. 6 data points highlighted. Our R square is relatively small, 9015. Okay, 9015 is between those two values, right? Okay.
Okay, that makes sense. Yeah.
Okay, so your lower value or minimum value for the CL is 0.99. And the other one is 0.999, 1 minus 10 to minus 3. Okay?
Okay, thank you.
Okay.
Professor,
yeah.
I finished everything beside the unit parts, I think. Can you teach me how to do the units?
Okay, your group number
3.
right?
Yeah.
3, group number 3?
Yeah. Mm-hmm.
Okay. Okay, which units are missing here for you?
On the very right hand
Those
side.
two?
No, the all the way right. The slope.
Okay,
Yeah,
right here.
Those yeah.
Okay, so the slope, the unit of the slope, right? Those
Yeah.
ones that you want, right?
Yes.
Okay. Is the rise over the run. The rise is kilogram square. The run is kilogram square.
Wait, hold on. It's the rise is kilogram square?
Well, yeah, here you go. You plotted, here you go. The first one, you plotted this graph here, right?
Mm-hmm.
This graph and this graph, right?
Mm-hmm.
What's the unit here for that?
That one is kilogram.
No, it's not kilograms.
It's not? Oh, okay.
It's not kilograms. Notice that the mass is squared, right?
Uh-huh.
The mass is square.
Mass square.
Without the square is kilogram, but with the square has to be something else.
Kilogram square?
Yeah. Yeah.
Is it?
Yeah.
Yeah.
And what about here?
That one as well, I think. Kilogram square.
The unit of the slope is kilogram square divided by kilogram square.
Okay.
Okay.
So do I need to type kilogram square?
Where? In the table?
No, for the the slope.
Well, what's kilogram square divided by kilogram square?
Kilogram?
Huh?
Kilogram square divided by. Well, I'm so sorry. Can you repeat the?
Yeah. Write that down with the paper, right? Pen and
Okay.
paper. Kilogram square divided by kilogram square.
Isn't it one?
Yeah, it's one. And that's what you write here. Okay? The units for the slope.
So it's one?
Yeah.
Oh, okay.
Okay.
Oh, but do I need to change the format?
Change the format.
Yeah, but I think it's scientific format.
No, you don't need to change the format.
Okay.
There you go. Yeah. Yeah. If you want, you can change it. Yeah. You don't have to. Because it's in scientific format.
What's the percentage difference from here?
Well, the percentage difference is, it's just the sign of percentage. Just the percentage sign. That's the unit for the percentage difference.
Okay. Intercept is y. Do I need to type y? No.
Well, I want you to look at the data, at the graph. And now for this one, I want you to look at the graph and figure out by yourself, okay? What's going to be the unit for the intercept? Okay. You can also look here at this equation here. Okay. Compare this equation with this equation. Okay.
Okay.
Here the slope is 1. And here is the intercept. Right? What's going to be the unit of this intercept that you see here?
Kilogram? Looks like
Huh?
oh no, kilogram square.
Yeah. Okay. Yes. So that's how you do. You gotta look at the equations, okay? To figure out what's gonna be the units that I'm asking for.
How about the tangent?
The tangent is just one. So tangent has no units whatsoever.
Also
It's less unit.
just blank space?
Huh? No blank space. You put one, number 1.
Oh, number 1. Okay.
Yeah.
Okay, let's see. What am I missing? I think I'm finished.
Okay, let me move forward, right? And then let's see here. I'm on Camden, right in here.
Yeah, I think I'm finished.
You finished
everything.
now? Okay. Okay, and what about Alexis? You finish, Alexis?
Yeah, I finished.
Okay, any questions?
No, I don't think so.
Okay, what about Marco Sanchez? Hello, Marco. Are you finished? Okay. Okay, so looks like most of you finished, right? And let's see, what about Catherine? Need any help there, Catherine? Okay. Okay. Okay, so okay, so if you wanna go, I think we're done, right? And we're gonna meet again Monday. And I'm going to start chapter 5 on Monday. Okay?
Professor,
Yeah.
when are you going to upload this week's lecture video?
What's the question?
When are you going to upload the this week lecture videos?
Okay, I will upload it. I'll try to upload it today.
Today? Oh, okay. Thank you. All right. Thank you so much. Have a good one.
You too. Bye-bye. I gotta go. Lá fora.